Hey everybody. So we've got some more trig identities or formulas here, and we're gonna come up with what we call the reduction formulas, starting with these um, the double angle formulas that we looked at in a previous video. And if we rearrange these equations, what I'm going to do is solve each one for the squared trig function. So in this case, I solve for cosine squared theta. We're going to get 1/2 1 plus cosine of 2 theta. And if we do the same thing here, solve for sine squared theta, we get 1/2 1 minus cosine of 2 theta. Okay, and these are what we call the reduction formulas. We also get another one. We can use these reduction formulas and the fact that tangent squared theta is equal to sine squared theta over cosine squared theta to get that tangent squared theta, right? We just plop these two formulas that we just came up with up here into the numerator and the denominator, and you end up with 1 minus cosine of 2 theta over 1 plus cosine of 2 theta. Okay. So these are pretty useful. Sometimes having squared terms or higher, we'll see in a minute how we can use these to get rid of things that are even higher, greater powers of the trig functions, can be really, really useful, right? So there's certain operations, for instance, when you get to integral calculus, you'll be taking something called the antiderivative of squared trig functions, and these reductions really make this possible. They make it a much simpler process than when we've got that exponent there. So they turn out to be pretty useful. Let's just do a couple of quick examples. For instance, let's start with something we know. So from the unit circle, well, if we were doing, excuse me, cosine squared of pi over 6, from the unit circle, we know that cosine of pi over 6 is root 3 over 2. We're squaring it, and we'd get 3/4. Let's just try to do this with the reduction formula, right? Not that this is particularly useful, but I find it sometimes nice to see that, just confirm that it at least aligns with what we know already, that this should be 1 plus cosine of 2 times pi over 6, right? Well, what's that? That's 1/2 1 plus cosine of pi over 3, which is 1/2 of 1 plus 1/2, right? Cosine of pi over 3 is 1/2. So that's 1/2 times 3/2 over 3/4. So obviously this isn't a simpler way to do it. Just kind of see that these things, at least to some give us some evidence that this is not just some made up manipulation. So let's do one more quick example of this one with one of these. Let's see how we could use this. Suppose we had something like sine to the 4th of x, and we wanted to write it without any powers of sine, so nothing higher than a power of 1, I should say. Well, we can start by rewriting this as sine squared x squared, right? Let me put in an extra step here, just because this notation is often very bad. Remember what sine to the sine 4th power x really means is this, which means we can write this as, that's rules of exponents. And then, of course, using this abusive notation on sine, this abusive notation here that we all use. In any event, we end up with sine squared of x squared. And then we just use the fact that sine squared of x is equal to 1/2, 1 minus cosine of 2x. Right, that's just our, I just replaced theta with x from the rule that we developed up here. All right, so what happens now? So let's come over here. Sine the 4th power of x. We have sine squared x squared. I'm going to replace the sine squared x with this configuration here. So I get 1/2, 1 minus cosine of 2x. So we can write this as 1/2 squared, 1 minus cosine of 2x squared. We get 1/4. If I square this, I'm going to have 1 minus 2 cosine of 2x. I'm just expanding this using the distributive property, and then we'll get plus cosine squared of 2x. Well, we still have a power of cosine bigger than 1 that we don't want, but I can use the rule that cosine squared of theta is equal to 1/2 of 1 minus cosine of 2 theta. Well, if I replace theta with 2x, oops, this should be a plus, right? So I'm just replacing the theta with 2x. If I replace this theta with 2x and then I've got the 2 sitting there, this will look like that. So I can rewrite this cosine squared as 1/2 1 plus cosine of 4x. Let's see. There. I think I got all of my parentheses. Maybe we want to expand things. I mean, this is correct as is, but maybe I'll write out 2 cosine of 2x plus 1/2 plus 1/2 cosine of 4x. And we'll have 1/4. I'll have 3/2 minus 2 cosine of 2x plus 1/2 cosine of 4x. And I end up with 3/8 minus 1/2 cosine of 2x plus 1/8 cosine of 4x. So really any of these versions down here are appropriate. They've satisfied the condition that we have no powers of trig functions greater than 1. Sometimes it's a good exercise to expand things. All right, that's it for this one. It's just another formula that we have in our toolbox. Like I said, we're going to kind of build all these identities up, and then we'll start using them together and try to practice and get good at manipulating them. And their real usefulness does come further on down your scientific career. And right now our job is just to understand how to use them and practice applying them a bit. Okay, that's it for this one. Thank you, everybody. I will see you next time.